All right, so let's do this. As the quiz implies, we got one more of these here, one more lecture, and we're going to finish our discussion of alpha carbon chemistry. All right, we're going to talk about first enones. Oh, no, you can't. It was going to be a in the dark lecture here. Trying that one out. No, my bad. So yes, enones is going to be our topic of discussion today. An enone is a ketone with a double bond in there, and specifically that double bond is going to be conjugated to that carbonyl group. All right, so this is an example of an enone, or more formally called an alpha beta unsaturated ketone. Or aldehyde, I guess, in this case. All right, and what's going to be unique about these enones is they actually have two electrophilic centers to them. One is our normal electrophilic carbonyl carbon. All right, but because of resonance, this beta carbon over here is also left with a lack of electron density. Remember, we had this numbering system or lettering system for our carbons in our ketones and aldehydes. We're starting from our carbonyl carbon. We move over. The next one is our alpha carbon. And the next one is our beta carbon. All right, so these enones, they have two electrophilic centers. That carbonyl carbon and that beta carbon. What we're going to see is that some nucleophiles prefer the one electrophilic site, the carbonyl carbon. Other nucleophiles prefer the other electrophilic site, the beta carbon. All right, just sort of generically, our mechanism here for that, what they call, for that beta carbon, we're going to take our alpha beta unsaturated ketone here, our aldehyde, our enone. All right, here's our nucleophile. We're just going to use generic nucleophile for right now. Again, that beta carbon is an electrophilic site, so this arrow is going to come down here and attack that carbon. Am I allowed to stop there? No, that carbon's got too many bonds now. So what's going to happen is this pair of electrons is going to be kicked over to this carbon. And am I allowed to stop there? No, same problem. So now we got to move this pair of electrons up onto that oxygen. All right, so now we have that nucleophile attached to that beta carbon. We have a new carbon-carbon double bond. It's moved over here. And now my oxygen has this negative charge. All right. We don't have any good leaving groups to kick off or anything like that. So our next step here will just be to protonate that oxygen. All right, but importantly, this does not stop here. All right, because what is this product that we've just formed here? We have a special name for this. With the double bond right next to the alcohol group. This is an enol. And what do we know about enols? They tautomerize. This equilibrium that very much so favors the other tautomer, the ketone. Or in this case, aldehyde. Right, so what we've done is we've added our nucleophile to the beta carbon of that compound, and we retain our carbonyl group. Cool. All right, so these are what we're going to call, these beta carbon additions here are what we're going to call Michael's additions. All right, so the alpha beta on the enone here is what we call our Michael's acceptors. And your Michael's acceptors, they can be enones. It's a little bit more broad than that, actually. We just need to have this double bond that's sitting next to some good electron withdrawing group. All right, and we got a bunch of our possible electron withdrawing groups here. Okay, pretty much anything with a carbonyl group in that position. So whether it's an aldehyde, a ketone, but it could also be our other carbonyl containing functional groups, like an ester, an amide, or carboxylic acid. All right, although a carboxylic acid is a good electron withdrawing group, we are going to scratch it from our list here because they're not really compatible with these Michael's reactions. So even though it does count as an electron withdrawing group, it doesn't work for this particular set of reactions. Two others to add to this list because they're a little bit more puzzling here are nitriles. These don't look the exact same, but we again have this high order bond to a more electronegative element. And then there's one really good electron withdrawing group that we've discussed before, that nitro group. This would also work. All right, so these are all going to be good Michael's acceptors, where you have this nice electrophilic beta carbon. Okay, our Michael's donors are going to be kind of the more surprising ones here, the nucleophiles that we're allowed to use in these reactions. It turns out, again, we have these two nucleophilic sites, right? The nucleophiles that prefer the beta carbon here, they're all very resonance stabilized negative charges. We don't really scratch the surface of it too much here in this level of organic chemistry, but there's this like hard-soft theory of nucleophiles and electrophiles where basically things that have a lot of charge density like to react with other things that have a lot of charge density, and things that have more spread out resonance stabilized charge density like to react with other things that have more resonance stabilized charge density. All right? This electrophilic center right here is only electrophilic because of the resonance of that double bond and that carbonyl group. So it's going to react with more resonance stabilized nucleophiles, again what we call Michael's donors. All right, our Michael's donors, what we're going to see is a lot of enolate ions, right? A lot of deprotonated alpha carbons. Okay, but again, it's got to be nice and super stabilized, so it's actually going to be sandwiched between not one, but two of those electron withdrawing carbonyl groups. Right, so here's a good example. Our Michael's donors here are going to have this generic structure where we have this carbanion between two electron withdrawing groups. All right, so here's a good example. Instead of being two aldehydes, we could have two ketones. All right, so here's some examples. It doesn't have to be aldehydes or ketones. We can have an ester or an amide. Any one of those electron withdrawing groups that we just listed on the other side, they can work here for these Michaels as well. They don't even have to be symmetrical. It could be an ester on one side, ketone on the other, etc., etc. I'm just going to put any of those electron withdrawing groups on either side of this alpha carbon. That's going to be our Michael's donor here. All right, so let's take one of these here and try to do an example. So here's my nucleophile. Here's my Michael's acceptor. I'll put another group on there. Let's make it an ester. All right, and everybody give me the product of our Michael's addition reaction. All right, my nucleophile here is just that alpha carbon. My electrophile here is that beta carbon. And in our reaction, we're going to form a new carbon-carbon bond between our nucleophile and our electrophile. Importantly, in the process, we will lose that carbon-carbon double bond. All right, one of the things that is going to make these reactions really sort of intimidating is we get these big, ugly products on the other side here, right? Anytime we're forming new carbon-carbon bonds, we're going to get a bigger molecule. And our Michaels donors, they got a bunch of functional groups going on, so they look all kind of crowded. Same thing with our Michaels acceptors. So our product here looks pretty intimidating. All we've done, though, is create a new carbon-carbon bond between that nucleophilic alpha carbon and that electrophilic electrophilic beta carbon, losing that double bond in the process. All right, and again, if we looked at our mechanism, we could explain that. Cool. All right, so again, a Michaels donor here. We got some examples going on. Importantly, when we have our Michaels donors, they have this carbanion sandwiched between two electron withdrawing groups. All right, there are two sort of notable exceptions here, things that are good Michaels donors, but don't follow that same logic of having these two electron withdrawing groups. One of them is just a nitroalkane here. That nitro group is a good electron withdrawing group. You could sandwich a carbon between two of them and it would be a great Michaels donor, but you actually only need one of them here because it's such a good electron withdrawing group that it really helps to stabilize that carbanion, right? So instead of having two, if you have that most crazy electron withdrawing group, the nitro group, you only need one. And the other is going to be a new organometallic compound that we're going to be introduced to here, what's called a Gilman reagent. So not a Grignard, but a Gilman. This has this formula R2CuLi. Okay, it's a copper lithium-based organometallic reagent, not magnesium bromine like our Grignard. Cool. All right, so let's talk about Gilman here for a second. Okay, this is again an organometallic reagent. And we want to think of it as a weak or a soft Grignard. It will also create new carbon-carbon bonds in the same way that our Grignard reagent does, but it prefers that beta carbon as opposed to that harder nucleophilic site, that carbonyl carbon. All right, so in fact, we're going to put these two next to one another. We're going to take an alpha-beta unsaturated ketone, or we'll just do the simple aldehyde. And we're going to show first what happens if we add in a Grignard. that Grignard is going to prefer, that Grignard is going, hard nucleophile, going to prefer that electrophilic carbonyl carbon. All right, so everybody take a second, draw me my product here of this reaction. So here that double bond doesn't even come into play. We just form a new bond between that electrophilic carbonyl carbon and that nucleophilic carbon of my Grignard. So now I have my new carbon-carbon double bond. All right, my Grignard was 3 carbons, so 1, 2, 3. And I need to protonate that oxygen. I get my alcohol product. Why doesn't this thing tautomerize? What's the difference between the position of our double bond here compared to what it was in our enol? It's right next to it, right? So this is an enol is when it's right next to that hydroxyl group. This is the one that will tautomerize to a ketone. This one is not in the correct position, right? So we don't have that same tautomerization. Crap, where am I? Oh, here we go. Cool, so that's stuck, it's there. All right, and now we're gonna do a new pathway here. But for our Gilman, so first of all, Gilmans, they have 2 alkyl groups on there. So if I'm gonna add this 3 carbon alkyl group here, I'm gonna show that there are 2 of them. Only one of them is ever involved in the reaction. One of them will stay stuck to the copper here. So this is that same nucleophilic 3 carbon chain here. Again, we're going to do our acidic workup. But again, the whole shtick about the Gilman is that it prefers instead this electrophilic beta carbon site here. All right, so instead give me the product if that Gilman was our nucleophile and our electrophile was that beta carbon. So instead now on the other side of my carbon-carbon double bond is again that nucleophilic carbon, but it's attached to the beta carbon. And I need a 3 carbon chain here. All right, so our Grignard is going to prefer that electrophilic carbonyl carbon. Our Gilman, again, creates a new carbon-carbon double bond, but it's going to prefer that electrophilic beta carbon. Which is what we call our Michael's donors, right? Things that prefer that site. So Michael's donors, most of them are going to have these 2 big electron withdrawing groups in the middle with the carbanion. Our Gilman is another example of something that will add to that electrophilic beta carbon. All right, one other thing that we're going to note here about our Michael's donors is in order to deprotonate, we don't have to use anything crazy. We made a big stink last lecture about how in order to create an enolate ion, we had to use a really strong base like sodium hydride or LDA. We don't have to worry about that in this case because it's sandwiched between these two carbonyl groups. These hydrogens are way more acidic than if I just had one electron withdrawing group. So they're actually fairly easy to remove. So we're just going to note here that we deprotonate with our cheap base, sodium hydroxide. Right? Those are really good acids. Those alpha carbons are way better acids than they are when you only have one electron withdrawing group. So we don't need to worry about going crazy. We can just use our cheap go-to base, sodium hydroxide. All right, so let's do another Michael's addition here. Bless you. All right, so we have this dione here. We're going to first add sodium hydroxide. Okay, then we're going to add in our enone. Okay, and then as we saw in our mechanism, we're going to have this last protonation step as well. So here's our sort of reagent list for these Michael's reactions. All right, so sodium hydroxide, what's that doing for me here? All it's doing is deprotonating that alpha carbon, giving me that enolate ion, that Michael's donor. And so now I'm going to form my new bond between my alpha carbon and that electrophilic beta carbon. All right, I'm going to have to try to scrunch this in here. My product of this Michael's addition here is going to have that new bond between the nucleophilic alpha carbon and that electrophilic beta carbon. All right. We got one more reaction to go here. All right, and actually, first thing, before we move on, one thing that I want to note about these enones, where we started off today, these are also, we've seen these before. These are the product of an aldol condensation. It's just always good to note when we got reactions that we can chain together here. This enone right here would be a product of one of those aldol condensation reactions, so we know how to make these enones. So we can make those enones, turn around and do this Michaels addition with it, and create our product of that Michaels addition. And now we're going to learn something that we can do with the product of those Michaels addition reactions. What's called a Robinson unylation. A Robinson unylation is an internal aldol addition. Aldol condensation. So those aldol reactions, but all taking place within the same molecule, right? One half of our molecule is going to react with the other half. These will always create a six-membered ring. All right, so again, we're going to start with our product here of our Michaels addition reaction. Okay, and the thing to note about this Michaels addition product here is we got a bunch of nucleophilic alpha carbons. And we also have a bunch of electrophilic carbonyl carbons all in the same molecule. All right, and again, that's what's going to happen is this molecule is going to react with itself to form this six-membered ring. Okay, in order for this to occur, what we're looking for is a alpha carbon that is exactly 6 carbons away from a carbonyl carbon, right? We need that perfect spacing in order to form our six-membered ring here. So if we looked at, for example, this one and said, all right, is this going to be a nucleophilic center here? 1, 2, 3, 4. No, it's too close to that carbonyl carbon. 1, 2, 3, 4. No, it's too close to that carbonyl carbon. So that's not going to work. All right, but if we look, and it's symmetric, so it doesn't matter which one we pick. If we look here, this alpha carbon is 1, 2, 3, 4, 5, 6 carbons away from our carbonyl carbon. And so what's going to happen is we're going to add in our conditions for our aldol condensation. All right, we're going to use sodium hydroxide. They use it in ethanol. And apply some heat. Okay, and what's going to happen, let me kind of get rid of my markings here. Try to unclutter this a little bit. Is that base is going to form that enolate ion, which is then going to tack that carbonyl carbon in the exact same molecule, right? So we have this internal aldol condensation reaction occur. This is going to create a six-membered ring. And this molecule is kind of kinked in this conformation already that might make it a little easier to see what our six-membered ring is going to do. But a good strategy here would be similar to what we did when we were doing our Diels-Alder reactions, where since I know it's going to form a six-membered ring, that's where I'm going to start out. And then I'm just going to number everything and fill in accordingly. So for example, on carbon 4, I know I need this ethyl group here. Carbon 2, there's that carbonyl carbon. And on carbon 3, have that whole ketone group. All right, so I've formed this 6-membered ring here. In order to fill in my molecule correctly, I went through and numbered my carbons, made sure I had that proper 6-carbon spacing, and then I decorated it. I am missing one thing, that carbonyl oxygen. If this was an aldol addition reaction, we'd have an OH group there, but it's an aldol condensation reaction, which means I'm going to get a carbon-carbon double bond. It's going to be conjugated to that carbonyl group. All right, if we number from our alpha carbon to our carbonyl carbon, we can just note a good double check. It'll always be between C1 and C6. All right. So our Robinson unylation reaction, it's an aldol condensation reaction, but an internal aldol condensation. 1/2 of your molecule, an alpha carbon from 1/2 of your molecule, reacts with a carbonyl carbon in the other half of the molecule. It will always form a 6-membered ring here. So what you're going to do is look for this 6-carbon spacing between an alpha carbon and a carbonyl carbon. That's your ring that will form, right? Again, that carbonyl carbon will, that alpha carbon will be deprotonated and react with that electrophilic carbonyl carbon. And again, this was our product of our Michaels addition reaction. So now let's just do a practice where we're going to chain these two together here. All right, Michaels and that Robinson. We're going to go NaOH. Going to do a alpha beta unsaturated ketone here. Then that acidic workup. All right, and our product is what we're going to then add our sodium hydroxide and ethanol and heat to. All right, and I'm going to sort of just warn you here that this is going to look a lot more like an internal, not aldol, but what was the other one? When we use our esters, a Claisen condensation. All right.
So just to clarify for the Robinson anylation, what happens to that other oxygen?
It'll come off as water, so similar to what happens in our aldol condensation. When you add that heat, that you get that dehydration reaction where that alcohol pops off. right? So these are really sort of a trust the process kind of reaction here because they produce these big intimidating products. Then we're going to have a hard time squeezing this in here. Whoops. All right, so here's my Michael's addition product where I've added my nucleophilic alpha carbon to that electrophilic beta carbon, right? Losing that carbon-carbon double bond in the process. So now I got to take this product here. I'm just going to rewrite it actually, make my life easier. And we're going to do this Robinson unylation with it. Okay, so now what I'm going to do is I'm going to go through and I'm going to color all my nucleophilic sites in red here. My alpha carbons, I only have these two. And I have these 3 electrophilic sites here. All right, and I'm looking for this perfect 6 carbon spacing. All right, so where do I have a nucleophile successfully located 6 carbons away from an electrophile? All right, 1, 2, 3, 4, 5, 6. So that's going to be my new ring. All right, so if we just kind of want to show our mechanism, that means that that base is going to deprotonate that alpha carbon. Which is then going to react internally with that carbonyl carbon at the other end of our molecule. All right, I'm going to do the mechanism here to prove a point. Again, the best way to kind of start connecting these things is to number 1, 2, 3, 4, 5, 6. And to create a ring, we know that this product's going to be a ring. And to number those carbons accordingly. 1, 2, 3, 4, 5, 6. All right, everybody take a second. Try to fill this in here. Right? So I wanted to do our mechanism here to sort of prove a point. I got to include what's on carbon 6, which following my electron pushing arrows would be an alkoxide ion and that ester substituent. Are we going to stop there? Are we stuck here? No, right? So we have our tetrahedral intermediate that we always have, but unlike with the aldols, our clasins are not stuck. That pair of electrons can come back down and kick off that leaving group. So everybody take a second and draw me the product of this reaction here. We've reformed that carbonyl bond on our carbon 6 here. Cool. All right, so very much so trust the process reactions that you have to practice drawing the products of. Nobody just looks at this and is like, totally, I get that. No, it's going to be like getting your hands dirty and going in there, pencil and paper studying. All right. Awesome. All right, good luck. So on Monday of next week, if you can make it, we'll have our review session for your exam. Monday is the only day that you have available to take that exam. On Wednesday of next week, the last day of class will be exam viewing. Cool.